In this video, we'll continue a discussion about the amount of voltage drop across circuit elements in alternating current. And in this case, we'll talk about the voltage drop across a capacitor. Now, capacitors are going to be a little interesting. So far, when we talked about voltage drop, we said, well, in the case of direct current, there's only 3 times that are kind of interesting to talk about. If you wait a very long time, the capacitor will become fully charged. Therefore, it will stop any current, and there'll be some set amount of voltage drop across it. And it'll come out to be the EMF of the battery. And in the meantime, it'll exponentially decay up towards a set value, or the remainder exponentially decay has that rise curve. And then in the case where you discharge it, it decays down to 0. And you can talk about the time constant and so on and describe what happens, but it basically came into charging up, discharging, and after a while, nothing happening, essentially. No current running and a constant EMF. But that wasn't the case where the current just tried to, we had a constant EMF source, a direct current source, meaning that the battery never changes EMF. But here, in alternating current, it's constantly changing. So it's constantly charging and discharging. And that'll change this story significantly and make it significantly more complex. So we'll try to figure out what happens if you are constantly charging and discharging and never letting it get fully charged. So what we're going to do is imagine we just hooked up a capacitor to this AC power supply, meaning that this is the EMF of this symbol here varies like a sine wave. What this will do is cause a current to flow through the circuit that will also vary like a sine wave. Now, the reason why I want to talk about current here is because the voltage drop across the capacitor is equal to the charge on the capacitor at the moment divided by the capacitance. And this comes from the definition of capacitance, where we said that the capacitance is just the voltage drop across the capacitor, is the charge divided by the voltage drop across the capacitor. And then if I just rearrange this, and again I'm going to use a lowercase v to mean at the moment for the charge at the moment. And the amount of charge that has built up on there is related to the current. And we're going to use this discussion to relate current and charge to voltage drop. So I'm going to try to draw 2 graphs on here. I'm going to try to draw the current. And I'm going to try over time. And I'm also going to try to draw the voltage drop across the capacitor over time. And I'm going to, with some foresight, choose to start my drawing of the current at maximum. Okay? So it'll look like a sine wave, or a cosine wave, if you will. That looks like this. And it continues on, but I'm just going to stop there for the purposes of my drawing. And I did this with a little bit of foresight about where I chose to start this vertical axis. It's not saying necessarily this is t equals 0, but where I'm starting my drawing. And the reason I did that is that this will lead to, when I run through this argument, the average charge on the capacitor being 0 over time, which is what you would expect, that since the current is running back and forth, and it's constantly charging and discharging and switching which one has the positive plate and which one has the negative plate, you would find that overall, on average, there's each plate is as often positive as it is negative in equal amounts. So we're going to go with that case. So what's happening? Well, imagine this current. Let's say that direction is positive current. Say the current flows to the right. That means that charge is building up on this plate. It's becoming more positive, and the plate on the right is becoming more negative as positive charge is pulled off to the right. And that will continue to happen as long as charge flows in that direction, which is to say that as long as this number here is positive. So the charge will continue to increase in larger and larger and larger and larger until we reach this point right here, where the current goes from being positive to negative, meaning it's going to flip from going to the right to the left. So if I say that I originally have no charge, then I have no voltage drop. And the charge will continue to increase. I'm going to drop down a dotted arrow to try to indicate that these times are the same until it reaches that time. And that'll be at a maximum. Because now, as this goes flowing in the other direction, in the negative direction, so to the left here, then this will become less positive, and this one will become more positive, as charge is ripped off of here and put onto there. And that'll continue until the current switches directions again, when it goes from negative to positive. So that's at this moment. So originally, it built up from no charge, maxed out at the moment where the current switched direction. Then what's going to happen is this will continue to go down until it reaches a minimum when the current then flows in the other direction. The reason why it's going to be negative is because this positive charge is going to run out, and then it's going to start to become negative as charge is continuing to be pulled off on that side. So it'll drop down from here, this is where it flipped from the right to the left, until it continues to flip again, until it flips again. And so on. And so here, the current will flip again, and it'll continue to become more and more positive charge on it until that time, and that'll be a maximum of the positive charge again. Like this. And what I want you to see is that this is also a sine wave. Now, you don't know necessarily this is exactly a sine wave. If you run through the calculus and take some derivatives of these formulas we have, you can show that indeed it is a sine wave and not something that's like, jaggedly up and down. But you can see that by matching the maximums and minimums with the time in which the current switches direction, left to right, we've discovered that there's an offset here. That this is what's called out of phase. Okay, so when current is at 0 is when the voltage is at a minimum max, because that's when current is 0 is when it switches direction, and that's when it stops increasing to the charge and starts decreasing the charge, and so that's when the amount of charge meets a max or a minimum. And it's shifted back in time. Okay, so like if you take if I took this curve, I would shift it to the right, and I could get a curve that looked like this. And the way we phrase that is we say that this lags. So the current reaches a maximum first, then the voltage drop later reaches a maximum. And we want to describe this, and the way we do that is if we could say, well, sine usually has angles that go into it, and how much does the angle have to be off by to now go from be this far behind, so from 0 to a maximum? And the answer is 90 degrees. Okay, so the argument, aka what gets plugged into the sine function, is offset by 90 degrees, or in other words, by pi over 2 in radians, and that's how much that a quarter of a full cycle is on a sine wave. A full cycle gives you 360 degrees, 1/4 of that is 90 degrees. Okay? So what we found is that no longer is it in sync. It's still a sine wave, but it's no longer in sync. So if I want to write the equation, I said I'm going to choose to still write my equation with the current being the same, because I want to use the same equation for all of the circuit elements because they all have the same current running through them. If we're going to put these later in series, which is where we're going towards. Here, though, the voltage drop then to be offset in that correct way has to be have a minus 90 degrees inside the sine function. Okay, so there's a shift in the voltages in that way. And that's the real difference between this and a capacitor and a resistor. When is it at its maximum no longer is the same.